In this video, we're going to work an example problem involving the remainder of an infinite sum, so the r sub n. In particular, for this problem, we're going to be estimating the r sub n based on a series that applies to the integral test. So remember, we're studying different ways of testing a series for convergence or divergence, and each one of those techniques, one of those ways, is going to come with its own method for estimating the r sub n. And so we just studied and worked example problems on the integral test for convergence. So we're going to work an example problem here involving, so this would be if you have any series that is eligible for the integral test, it satisfies the criteria of continuous, positive, and decreasing, then you can use this method that we're about to do here for estimating the r sub n. If you have a series that's not eligible for the integral test criteria, then you can't use this method for estimating the r sub n. Okay, so use the sum of the first 10 terms to estimate the sum of the series, n is equal to 1 to infinity, 1 over n squared, and then how good is this estimate? So we're going to do the first 10 terms, but you could imagine in practice you would put this into like a software, and you wouldn't just do 10 terms, you'd do the first 5,000 terms or something like that. But let's take a look at the first 10 terms. So, okay, so the s sub n here is the sum from I is equal to 1 to n of 1 over n squared. This is a p series. We know this is convergent, right? This is a p series with p equal to 2, which is greater than 1. So this is convergent. Okay, so we didn't use the integral test to show that this is convergent. Well, actually, the p series, we did use the integral test to develop that theorem. But even if you happen to use in the future, if you happen to use a method for determining the convergence of a series that's not the integral test, that doesn't mean you can't use this integral test method for estimating the magnitude of r sub n. You just need to see, is this, so okay, this is going from, we look at the f of x. Okay, this is positive for x is equal to 1 to infinity. It's continuous and it's decreasing. So this is eligible for both the integral test and for we can use the r sub n technique, estimation technique. Okay, so, but we want to do s sub 10 here. So this is going to be 1 over 1 plus 1 over 4 plus 1 over 9 plus 1 over 16 plus 1 over 25. Okay. Okay. 1.54977. Okay, now how good is this estimate? So how good is this? How close is this to S, where S would be we know this is convergent. This is an actual value. Well, we need to get the r sub n. So if we have a series that is eligible for the integral test, then we take the f of x, so this is the f of x, and we integrate from n plus 1 to infinity of f of x. That's the lower bound of r sub n, and then n to infinity is the upper bound. And in the textbook, we talked about exactly where this comes from. All right, so n plus 1 to infinity, so n here is 10. So the limit okay. The limit as t approaches infinity of minus 1 over t from 11 to t. Or no, this is x. Okay. So minus 1 over x minus 1 over 11. So plus 1 over 11. Oh, no, we got to input the t. So this is equal to 1 over 11. So this is equal to 1 over 11. Okay, now from n to infinity, and we can see this is just going to be equal to the limit as t approaches infinity of, right, exact same as what we just did. So, okay. So r of 10 is less than or equal to 1 over 10 and is greater than or equal to 1 over 11. So, but what does this mean, though? We need to answer the question, how good is this estimate? If we just gave this to somebody, they wouldn't know what we're talking about. So what this means, so remember, what this means is that we've got this S of 10 here, and then, but the actual sum, we know that there is an infinite sum. The actual sum is this S of 10 plus all this other stuff going off to infinity. That's the R sub 10. It's telling us that the sum of all this other stuff is something between 1/10 and 1/11 inclusive. And so what you can think about is that you can say it this way. You can say that, so all of this is no bigger than 1/10. So the farthest off we are, like we know this is less than the actual sum for sure, because we're summing the first n terms. So this is at worst 1/10 off. So 0.1. Okay, so we can look at it this way. We could say take 0.1 and divide it by this. 6.5%, approximately 6.5% accurate. Now you might be saying, well, that doesn't seem too accurate. We just did 10 terms here. Think about with a computer, you could do 5,000 or you could do 5 million. You get really accurate. Okay, now it says improve this estimate using, it says 3 with n is equal to 10. So what they're talking about here is that you can, for any time you, if you think about it, you could do this with any, it's not like you could only do this with the integral test. It's any time as long as you've got an estimate for what the R sub n is. But, okay, so we've got an upper and lower bound on what so let's erase this. On what the sum of the remaining terms are. And so you can think about it, with that, we've got an upper and lower bound on the actual sum. So we can say this, the S of 10, if we add 1/10, so 0.1 to, let's come here, $1.64977. Okay, and then and then we do 1/11 plus that. $1.64068. Right? You see what we just did? We added the, like, okay, just to make sure this is clear, the R sub n was 1/10 to 1/11. Okay, that's the sum of all this extra stuff is equal to, it's something between 1/10 and 1/11 inclusive. So we can say, okay, well, then the actual sum, the infinite sum, we could say this S of 10 plus 1/10. It could be that. That's the upper bound, but then it could be S of 10 plus this. And so we get the actual, what S of 10 is. It's something between these two values, right? That makes sense. Okay, so, okay, who cares though? What's the trick? Well, how are we going to improve? How are we going to improve that? It was the 6.4% estimate or 6.5%. How are we going to improve that? What we can do is, so just remember what we're saying here, okay? I put approximately equal to because we didn't use the actual fraction. But really what we're doing here is, not only is this an approximation for the S of 10, but we're using this to approximate S, right? If we had the exact value of the infinite sum, we wouldn't use this. We just go ahead and use that value, right? So what we can do is we can, well, okay, no, this is not, okay, I messed this up. This is not S of 10, this is S. That's absolutely not S of 10, this is S. We added 1/10 to S of 10 and 1/11 to S of 10. So this is the estimation of the actual S. This is what we want, right? We're looking for S. We don't care about S of 10. If we had the S, we just go ahead and use that instead of this. So how can we want to replace this with something more accurate if we can, that's closer to the actual S? Well, we could just take the midpoint of these two. So it's this plus this divided by 2, 1.64522. You see? And if we had S of 1,000, we would get we'd shrink this range of estimation on the S. And so now what's our accuracy? Now our accuracy is 1/2. So previously we were off by at worst 1/10. Now we're off by at most half of the length of this interval. So that's this minus this divided by 2. Now we're off by at most, or no, wait. $1.64977 minus divided by 2. Now we're off by at most this much. So that's a big improvement. And we can do the same thing. We can divide that by 1.54977, 0.3%. Right? And that's really powerful. Just with the S of 10 and the remainder estimate, we were able to get a value that's within 0.3%. So imagine if we did S of 1,000, then just the initial value would be within, let's say, 0.3%. But then when you did the improvement method, you'd get it really accurate. But if you did S of 500,000, then you could just be plenty enough accuracy for like an actual application. Okay, so they calculated this infinite sum in exercise 34, and they got pi squared over 6 is the exact sum. So, okay. $1.64493 is pretty good. And so we're at worst 0.3% away according to the remainder theorem, but let's see how much we were actually away. So this divided by 1.64522 we were actually 0.02% away. So we knew we were at worst 0.3% away, but we were actually 0.02% away. Now, the value, you can see that the value we got, 1.64522, is greater than the actual sum value. And you might be confused thinking, well, I thought, how could we estimate a higher value? Well, yeah, the partial sum, the S of whatever we plug in, that's always going to be less than the actual sum. But when we got the R sub n, there was a upper and a lower limit on what the R sub n can be. So once we added that to our S sub 10, then we knew the sum was somewhere in this range. So what the actual sum is compared to what our estimate is, in this case, it could be above or below. It's random, right? We know the sum is somewhere in between this range. This was our estimate. And so where the actual sum ends up being, it might be above or below this, what our estimate it was. Okay, now last question is we want to find a value of n that will ensure that the error in the approximation is less than 0.001. All right, so we're not going to get into the whole process of improving on the estimate, with the getting the range of what the infinite sum could be and dividing by 2 and all that. We're just going to look at it from this standpoint. So the R sub n, if the upper range, the upper limit on it, this is, depending on the value of n we choose, this is the worst we could be in terms of not a percentage, but in terms of magnitude away from the actual sum. That's what they're asking us about. What value of n do we choose to where at worst the error is going to be the error in terms of how far you are off from the actual infinite sum, not as a percentage, but as a magnitude, is no worse than 0.001. We could just look at this here. Okay, so we want to say that the upper limit is going to be from n to infinity of 1 over x squared dx needs to be equal to some value. And I think we have to use a bunch of variables to actually go that extra step. You could do it, but I don't think the question's asking us to go that far, to go that deep into it. But we would have to, okay, we could just stop here and say this needs to be equal to 0.001. Solve for n, and as long as n is equal to or greater than that value, then the error will never be any larger than this. But you could lower that requirement for that n even further by, we would have to say that this is, so we would call this R upper, and then we do the same thing with R lower, and then we would have an S sub n as well, and then we would add the S sub n, and that's a going all the way to the improvement step with this final question. I think it's beyond the scope of this problem, but you could think about doing that, and maybe I'll make a separate video on that. Okay, but let's just do this. Okay, this still is, we're going to get a valid answer to this question doing it this way. So, okay, we've got the limit as t approaches infinity of n to t Okay, so we've got the limit as t approaches infinity of, we could take out the minus, 1 over x evaluated from n to t. Okay, let's just keep going here. So we've got minus the limit as t approaches infinity of 1 over t minus 1 over n. This is equal to minus 1 over n, so 1 over n, which is equal to 0.001. What is 1 divided by 0.001? 1,000. So if n is greater than or equal to 1,000, then you will have a error of magnitude that's less than or equal to this. Now, I'm curious about if we could have done this, gone that extra step. So what would have happened is, let's see. If we did go that extra step, what would have happened? So that means that this is equal to the R upper. All right? This is equal to the R upper. Now, if we go from n plus 1 to infinity, what happens? We get everything's the same except the limits of integration. So are lower. Okay? So so we got our upper is 1 over n, our lower is 1 over n plus 1. Okay, and this is probably not going to work, and the reason why, now that I'm thinking about it, is because we need an S of n formula. And with these problems, these convergence problems, that's the case is that we don't have an S of n formula. If we had an S of n formula, then we wouldn't need to do any of this, right? Because we would say, what we would do is we've got R sub n is less than or equal to 1 over n. And then what we would do from here is we would add S of n to all sides of this. S sub n plus R of n, R sub n is S, right? And then from here, we would take the range of these upper and lower limits, and divide by 2. This might work, actually. Because what we do is we say this minus this divided by 2, and the S of n subtract out, right? S of n plus 1 over n minus S of n plus 1 over n plus 1 is equal to 1 over n minus, and then you divide that by 2, and then we want this to be equal to 0.001, right? Okay, yeah, so this will work. Let's just put this into the calculator. So this video is getting a little long. So 1 over 2 times n, and then 1 over 2 times n plus 1 that minus that, store that as E. Okay, so now we want to, we want to solve for E is equal to 0.001 for n. Yeah, look at that. So 22, round up to 22. So n is equal to 22. Instead of n is equal to 1,000, if you went that extra step and got the range, the range of the s, and then divide that range by 2, then you'd get something that would be less than 0.001, as long as you use something that n is 22 or greater. That's pretty cool.